All right, welcome everyone to discussion number 4's mini lecture. Today's mini lecture will be a little bit longer. We'll be covering 3 different topics. We'll go over regex, visualizations, and kernel density estimates, so KDE. Let's jump right in with regex, or regex, however you want to pronounce it. Regular expressions. So we use these when we're trying to parse string data, text data, and there are 2 building blocks to any regex pattern: literal characters and special characters. So literal characters are literally the character they represent. Most often we'll think of like A to Z, 0 to 9. So this example here, regex pattern that says bears, will match the text bears in other strings that we're searching in. The main part about regular expressions that makes it interesting are the special characters that allow regex to capture strings that aren't necessarily an exact match, but you could think of it as following a certain pattern. We can find strings that match a certain pattern, and that's probably why we call these regex patterns. So it's going to be a little dense today, but let's look at a little bit of the special characters. So here, the first one we're looking at is or. So we could say we want to capture AA or BAAB. So we'd match those 2 things, and anything else would simply not match. Closure is what we call the asterisk. So this just means having 0 or more of whatever directly precedes the asterisk. So if we have this regex pattern, the asterisk applies only to what's right before it, so to the B. So we can match 0 or more B's in this case. So we have to have the A and the A, and then we can have any number of B's. So we could have AA with no B's, A with a bunch of B's, A. We could also have ABA as another example. And then these would not match. Here we are missing an A at the end, and here we have some non-B in the middle. Okay, the next third one we can have are parentheses. This represents a group. So here, it's kind of like in regular math, the way parentheses can group things or tell you to do them first. You'll notice that in order of operations for regex, groups come first, just like in math. So if we're looking at this case here, which is similar to up here, but now we've inserted a set of parentheses. Now the or only applies inside the parentheses. So we're looking for an A or a B at this point, and then we have to have these other characters beside it. So here we can either match an A as the second character or a B as a second character, and nothing else would match. Okay, here's another example. And you'll see how we have this grouped AB, and now this asterisk is going to apply to whatever is directly preceding it. So in this case, it's an entire group. So now instead of just applying to the B like it did before, it'll apply to the entire group AB. And so we can either match 0 ABs, which is this example, or we can match a bunch of ABs or 1, or, so we have AB, 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 and then we have that last A. We could also have like 1 AB and then an A, or 2 ABs and then an A, and then these are just some examples of what would not match. So this screenshot here is from the course notes. So I would recommend kind of using this as a good reference. It mentions at the bottom, right, so this comment here at the bottom just kind of points out, right, that we have this order of operations that I've been implying and kind of comparing as we go through, and it's important to be able to differentiate the difference between things like this and with the parentheses, without the parentheses, right? So it is important to know that order. Okay, some other special characters. Here we have the period. It's any character other than a new line. So in this case, we could have any character in these 4 spots. So some examples would be having C, M, L, and S, or J, G, L, and M. You can really have anything there. You just have to have a single character, any character other than the new line, replace that dot. And the second thing we're going to look at on this slide are character classes. So these can be very useful. Basically, you match any one character inside the brackets. So we'll look on the next slide at some other defined character classes. But writing A to Z inside of a character class is defined as being all those characters, so all uppercase letters or lowercase letters. So match one character here, and then using the asterisk, we're saying any number, 0 or more, of lowercase letters after this. So here we have, this would match the W, then we have 3 other lowercase letters, then here we have the C being matched here, and then a bunch of lowercase letters. Here, this wouldn't pass, right, because the uppercase letter can only be the first character, and then after that, only lowercase are allowed, so this would not work. And then here we have a numeric number, right, which is not A to Z. Next, we have curly brackets, which we can use to define an exact number of times if we want something to repeat more definitively. Here we have a character class of vowels that we just defined. So we can have exactly three vowels is what we're looking for with this pattern here. So we have the J, three vowels, and then HN, or we can have the J, three vowels, HN, where different sets of vowels are all fine, but you have to have exactly three vowels, so these other ones wouldn't work. You can also have it repeated from A to B times, like a range of repeat numbers. So here we want it to repeat 1 to 2 times. We can have either an O or a U 1 to 2 times. So here we have one O, here we have two U's or O's, and then these other cases wouldn't pass. Here we have 0, here we have 3, so that wouldn't work. Here's another one. So this is similar to the asterisk, except instead of 0 or more, it's 1 or more. So here we want 1 or more of what is exactly preceding it, which is the O. So we could have one O, a bunch of O's, and then we can have 0 or 1 using a question mark. So you can have 0 or 1 H's. Here we have 0 H's, here we have 1 H, and nothing else would match. So there's really a lot going on here, and you'll just have to practice it to kind of get used to it. Like we mentioned before, we have the character class, super important. Here's another example, right? And I mentioned before, we have some built-in character classes. So the A to Z's, capital and lowercase, as well as digits 0 to 9. These character classes, you don't put inside square brackets. They just automatically represent what is written here. So /W, \W would be alphanumeric values, \D would be numeric digits, \S is white space, and you can look at the specific definitions on the reference sheet as well. We use a caret inside character classes to negate the character class. This is specifically when it's inside square brackets. So this basically means not. Anything other than lowercase a to z. So we could have numbers, we could have capitals, but we just cannot have a to z. Any one character that is not whatever I've written inside my character class. And a good thing that maybe some of you all are thinking about, well, if the period represents any character, how could I actually match a period? So you often need to escape special characters. If you want to read a special character literally rather than its special meaning, you'll need to use a backslash. So backslash period will let you actually match a period rather than it representing any character other than the new line. Here's another meaning of the caret. When the caret is not inside square brackets, it represents the start of a string. So you can see here, if we have the caret at the front, we have the $sign, which represents the end of a string at the end. That means that we need bears to be directly bears, right? B should be at the front of the string, S should be at the end. We can't do go bears with an exclamation point at the end or go at the front because the B and the S are no longer at the start and end of the string. All right, so where can we use these regex functions? There are many different ways to use regex functions. The one that I'll focus on right now is findAll, just because I think that's probably what we use most often, but it isn't the only place we use regex functions. But what findAll does is returns a list of all matches for the given pattern in the string. So we give the regex pattern, and then we also give the string we're searching for matching that pattern in. Something to note is when you write regex patterns, if you write special characters to be looked at as special and not just literal characters, you'll need to include this R in front of the string. So you'll notice that this is how we write regex patterns. Another important thing that you need to know for some of these functions are what capture groups are. So we talked before about parentheses and how they come up in regex as just like a way of grouping things together, kind of utilizing order of operations based on what you want to happen. Another way that parentheses are used are for capture groups. So let's just take a look at this example and I'll explain it as we go. So if we're looking at this pattern example here, right, if we zoom in, we're looking for 2 digits, a colon, 2 digits, a colon, and then 2 digits. This is our example text here that we're going to be searching for. So you can see that we're going to match right these two parts of this text. And what you'll notice is what read.findAll returns isn't the entire thing, but rather what's inside the parentheses or what's inside the capture groups. So here we have, right, the 3 things that were inside capture groups in the first match, and then the 3 things that were inside the capture groups for the second match. So it's important to keep capture groups in mind because these will inform what exactly read.findAll returns. The colons are still important because they're required to even get a match overall, right? We need the entire pattern to match. Once it matches, these parentheses tell read.findAll what we want to capture from that match. So this is using the re library. We also are able to do this in pandas. So it makes sense when we're talking about databases that we would want to be able to apply these functions to entire columns of string data. For example, just like we talked about with pandas, stir accessories, right? We can do something very similar in pandas using .stir still. So we'll do .stir and find all, and then we can put the pattern, and it'll look for this pattern inside of the entire series, which, for example, could be some data frame and some column, right? This would return a series on which we could do .stir, .find all, right? And then it'll return a series of the results of find all. So we'd have a series of all these results, for example. So that is very useful and will be most likely on homework problems and so on and so forth. So you'll get some good practice with that as well as in discussion. Definitely in terms of like regex resources, right? If always we have the documentation, right? So for example, for these other functions here, you can always go to the documentation to read more about them. We also have the debugging guide up on our site already, so you can look at that if you're having debugging issues. Whenever you're writing a regex pattern, especially when you're first learning regex, it can be super beneficial to practice with regex101.com. You got to remember to change the flavor to Python before you get started so it matches with the behavior in the Jupyter notebook. But once you do that, you can put in the text and put in and like start typing your pattern live and seeing what exactly it matches, what's in capture groups, and so on and so forth. It gives pretty nice descriptions on the side. Another thing, like for everything we learn in this class, it's good to look at what you'll have on the reference sheet, so you can check out past semester's exam reference sheet under resources on the website to see like what type of stuff is listed under regex and so on. So let's move on to data visualization. So plotting pipelines. In Data 100, we mostly talk about plotting with matplotlib and Seaborn. Usually these are imported as PLT and SNS. So in matplotlib, we always plot arrays of x versus y. So you have to give the function, right, an array for what should be corresponding to the x-axis, an array for what would be corresponding to the y-axis, if both are necessary for this plot. Versus in Seaborn, you can do that, right? You can provide it with arrays, but Seaborn also lets you provide it with entire data frames and then just specify which columns to look at. So it's a small difference, but it is a difference between matplotlib and Seaborn. In both cases, we usually use matplotlib to label our axes and add the title. Yes, okay. So let's look at how we pick which plot we want to use. So there's so many different types of plots, so I'll just kind of briefly go over what kind of tells me I want to use a certain type of plot. So here we're looking at if we're looking at a single variable, we can kind of look at what type that variable is to give us some intuition as to what plot makes sense. So if we're looking at a single qualitative, right, a categorical variable, we would most likely be going with a bar plot. Right? So this is an example. Let's say we have red, blue, green, something, maybe the counts of red, blue, green marbles, right? We would plot it as a bar plot. This is just an example of what that might look like. You could also theoretically put categorical variables into pie charts like this, but we usually try to avoid those because we aren't too good at looking at angles with our eyes. We, as in humans, aren't too good at looking at differentiating angles. The next distribution we might want to show is of a single continuous quantitative variable, right? So now we're looking at quantitative rather than categorical, and this is where we would shift from a bar plot to now a histogram, which shows a distribution. Histograms are super common, right? This is a good one to know. Another way that you could show the distribution is using a box plot or a violin plot. So in a box plot, right, on this side, a box, or sometimes called a whisker plot, the width of the box, like this dimension here, doesn't mean anything. Versus in a violin plot, the width indicates the density of the distribution at each possible value. So it's a little bit more specific here. You can see, right, this is more dense than other parts, and that has meaning here relating to the density. Both of them can be used to display the distribution of a variable using information about quartiles. So in the box plot, right, we have these lines, the edges of the box, this line. Here we have corresponding, we have this as the middle line. This middle line corresponds to the dot here. Then we have the edges of the box as so. And then this like edge of the line, it kind of all relates. So we still have information of the box plot and the violin plot. We just have the extra added information about density. So I've included this kind of all these details here for your reference. It's good to know, potentially it's been on past exams, so worth studying. In this middle, as this middle line, right, we're looking at the second quartile or the median. The outer lines are the third and first quartiles, also called the lower and upper quartiles. So the 75th percentile and 25th percentile, right, that means like 25% or 25% of the data is below this line. 75% is below this top line. And then these whiskers, they've been defined as the lower quartile minus 1.5 times the interquartile range, the IQR, which is the upper quartile minus the lower quartile. So a little bit of math here. But you subtract 1.5 times this interquartile range, then you add 1.5 times the interquartile range to get the upper whisker. And then everything left over, these are outliers. Okay, moving on. So now if we're looking at two variables, we want to consider some other options. So if we're plotting two quantitative continuous variables against each other, we have some options. We have a scatter plot, a hex plot, a 2D KDE contour plot. This is kind of more for your reference. I won't go in detail just because this lecture will get pretty long. If we're looking at a qualitative and a quantitative, so now we have a categorical and a continuous variable, you could imagine, like, for example, we're trying to look at the distribution of temperature across different states, maybe in a year, right? We have all the daily temperatures, but we want to split it up by state across the United States. We could have a histogram, overlaid histograms for every state. So there'd be one histogram per state, and they could be overlaid. Maybe 50 is a bit much, but you get what I mean. You could also have side-by-side box and violin plots. So you'll see we're using the histogram box violin plots to show, right, the distribution of a single quantitative continuous variable like we talked about before. And we're adding in the categorical part by just having multiple of them side by side, one for each category. So that could be like we have a number of these lie side by side showing different categories next to each other. If we're plotting time data, we want to most likely go with a line plot. So this is just for your reference to kind of help guide you, help summarize all the different types of plots we've learned. What makes a good visualization? The main thing we want to really hammer in on in this class is you need a title, axis labels, and oftentimes a legend. You want to make sure that if I have never seen your visualization before, I know what it's displaying. That's definitely something readers will ask themselves when grading your homework. They'll be looking at, did you label your axes? Do I even know what's on this plot, right? So that's an important thing to really keep in mind for this class. Some other considerations to think about: appropriate scale. Are the units consistent? Is it clear? Like, are the axes clear? Are they deceiving? You want to make it as clear as possible. You could think about colors, and in general, we want to avoid angles or areas if possible because humans aren't too great at telling the difference there. Okay, moving on to kernel density estimation, KDE. Okay, so what exactly is KDE? KDE is a smooth, continuous function that approximates a curve. It allows us to represent general trends in a distribution without focusing too much on the details. And specifically, it takes in our data points, right? So this is an example of our data points. We have 4 data points. It takes in those data points that we've collected and tries to approximate the underlying probability distribution. So what is a probability distribution? So a probability distribution is a description of how likely it is for us to sample a particular value in our data set. So this is the approximate probability distribution that we got using KDE. And you can see basically what it's showing us is that at these values, we expect, right, the probability of getting a number in this range in our sample is basically 0. So we're saying like anything below 1, basically 0 chance of getting it. That's our approximate. This is our guess as to what the underlying probability distribution is. Anything over 5, I don't think we're going to get it. That's what the KDE is saying. Perhaps because we don't have any points in our data that are that far. So it's unlikely. That's kind of what we're approximating here. That's our approximation. I think it's way more likely to get something around 3, maybe around 4, but perhaps less likely than numbers in this range. But that's what we use the KDE to try and get an approximation of, right? This isn't, of course, it's not completely the exact probability distribution, but it can be a helpful approximation. So basically, wherever there are more points in our sample, that's where we'll get higher probabilities in our probability distribution. So how do we go from just having data points to having a kernel density estimate? We first choose a kernel. So a kernel is the function that decides how much weight we give each data point. So the most common ones we'll talk about in this class are a Gaussian kernel and a boxcar kernel. After we choose the kernel, so we put these kernels over every single data point we have before we add all the kernels together. And in order to kind of make sure things make sense, we do need to normalize, and I'll show this more clearly in a coming slide. Before we get to that, another thing we need to choose about our kernel is the bandwidth parameter, which is oftentimes called alpha. So this alpha represents how smooth our curve is going to be. So in a Gaussian kernel, the bandwidth alpha is the standard deviation of the normal curve. So you can see here, if the bandwidth is 0.5, then we have a wider curve. If the bandwidth is smaller, then we have a thinner curve because the standard deviation is smaller. So the bigger alpha is, the wider our kernel. And you'll see on the next slide and in practice and discussion that this makes a smoother graph. So let's kind of look at it all together to really get a better idea of how this works. So we have our various points. These are just one line per data point. The first step is to place a kernel at every single one of those data points. So we chose our kernel as Gaussian in this case. There's some alpha we chose. We won't talk too much about that just yet, but there's some alpha. We put a Gaussian kernel over every single point that we have. Right now, each kernel has an area of 1. But we want, right, a probability distribution. Since our final curve is going to be a probability distribution function, it should, in total, add up to 1. All probabilities, right, should add up to 1 to make sense. So right now, if we just added these all together, we would get a function that has an area under the curve of 5, which is more than 1 and would not be a probability distribution. So we have to normalize the kernels. And this ends up being where we divide by basically the number of kernels. So right now the area of the blue kernel is 1. We're going to divide it by 5 so that the area of each kernel is now 1 over 5. So that when we sum it all up, the distributions will add to 1. So the idea here is, right, because of the probability distribution, we have to think about how we're going to make it all add up to 1. So once we've normalized, we can add all the functions together. So where there's overlap, right, it'll get taller. Where there isn't, it won't. And this is our final curve, a probability distribution function. There's a lot going on here, but there is an equation. We'll try to understand it together. So let's go through this kind of complex equation step by step. So let's start off here in the middle. The first thing we can look at is the k. So k, right, k is the kernel function that we chose. That could be Gaussian, it could be boxcar, it could be something else. Alpha, right, is that bandwidth parameter that we discussed. And then this kernel is plotted over every point, right? Every single data point that we chose, we're going to have a kernel centered on each of those data points. So this xi is telling us where the kernel is going to be centered. And this I goes from number 1 to n, where n is the number of data points. So we'll have a kernel centered at every xi, or every data point. And just like any function, right, if you think f of x, right, you give it the x and it tells you where the y is. We have the same thing here. So this function, right, you could look at an example. Let's say we're looking at the Gaussian kernel with alpha 1, right, centered at 2, because that is our first, let's say that's our first data point, is centered at 2. Then this is our function. So we'll be able to plot this by giving it every value of x and seeing what y is returned, like a regular function. So you don't really need to overcomplicate this in your head. We're telling it where to center it. We're telling it what kind of kernel it's going to be. And this x is just like the x in a regular function. You provided an x and it tells you where the y is going to be. That's how we get this plot. And we would do that, right, for every single every single observation or every data point. And right now, the kernel has an area of 1. That's how kernels are defined. They just come with an area of 1. Okay, so the next part we're going to look at is this 1 over n here. Because each of them have an area of 1, we need to normalize. So here we are dividing by the number of data points like we talked about on the previous slide. So in this case, we would be dividing by 5, right? Or you could say dividing by 5 is the same as multiplying by 1 over 5 to normalize the kernels so that later when we add them up, we'll get an entire area of 1, which is what's required for a probability distribution. And the last part here, right, is that we add these all up from 1 to n, all the data points. So we sum up the kernels for all the data points to get our final probability distribution. So it can be a little confusing at first, but hopefully this walkthrough was a little bit helpful. Please definitely come to office hours, go to discussion, talk to your TA, and ask some questions about KDE. If you have any, feel free to ask questions on Ed. And yeah, I hope that was helpful. Have a good discussion number 4. Bye.